going to be. Um, Welcome to the November 2021 edition of the Utah Forge Modeling and Simulation Forum. I'm Rob Gorney. I lead the modeling and simulation team for the Utah Forge project. As in the past forums, we'll kind of keep the same format. We have a set of speakers. I'll give a brief update of the site activities that are going on and where we're at right now, followed by a presentation. If you have questions, I'd ask that you stay muted if you can and type your questions in the chat box. We'll save the questions towards the very end. As we get time at the end, we will actually can go off mute and have more of a conversation. We have essentially this virtual room for 2 hours. I think we have these things scheduled for 90 minutes in general, but we'll probably have about a 45-minute presentation from our guests today, and then we'll go from there. So welcome. So I just want to talk a little bit scheduling. So, we are here in November. Today's topic is on the topic. Today's talk is on the topic of hybrid fracture matrix modeling for well completion evaluation. I'll introduce more of that later. It's very similar. You'll see a lot of those of you who were at the GRC meeting. A lot of the early parts of this presentation will be coming right from there, followed by a bigger update from Lynn and the team. Next month in December, we will have our guest is Federico Ciaro from ETH in Zurich, talking about injection rate ramp up, nucleation, and arrest of dynamic fault slip. ETH Zurich are doing some detailed collaborations with Utah Forge on a number of topic areas, and this is one of them. January, I'll just kind of give a wrap up of the 2021 and give a 2022 look ahead. So, general update. You've all seen this photograph before. This is essentially the state of the site itself. Things that are in white are complete. So if it's a well and it's labeled in white, it is drilled, it is done, it is in service. In yellow is a well that is planned. No new changes have happened at the site as far as this image since our last modeling simulation forum. There are a few things modeling related that I just wanted to give an update on. Is we did update and finalize the revision of the native state model. If you recall, we were waiting on the well 78B, which was drilled to about 9,500 feet measured depth. We finally got an equilibrated temperature log from that well, so we're able to include that, incorporate into the calibration. So we consider that modeling revision complete. Stimulation modeling is also complete. It's being post-processed. I'll show a few images of that. Strain modeling is underway to help look at where we might see the most strain for some of the planned strain gauge installations at the site. And once again, the stimulation last time I'd said it was planned for January of 2022. I believe that slipped a little bit into early February of 2022. So just real briefly, the native state model, I just wanted to show a quick few images. I'm not going to talk about any of this stuff in detail. What you're seeing on the left is just a simple plot of the model domain, which goes all the way to the land surface now. That is the wash, the Maglee wash coming through the site. Land surface down to a depth, I forget what the bottom elevation is, but it's about 4 kilometers on each side of the model. This is just DVR stress at the native state and a temperature profile, a temperature distribution in the granitoid body itself. That shows the mapped contact that we have between the granite and the alluvium at the site. A few temperature logs are shown here. Measured is in the red and the orange dots. The model is in the blue lines, just showing that a few of the deeper wells here, 56, 16A, and this is elevation versus temperatures in degrees Celsius. This is not measured depth, it is elevation. That is why 16A looks shorter than some of the other wells. It's actually the longest running well at the site. But I won't comment these in general, just that we have a pretty strong match. We're pretty happy with our calibration, and we're moving forward with it. For the simulation modeling, we've done a number of cases. So we did prepare as a team a stimulation plan for 3 different zones near the toe of well 16A. And we ran, I believe, and Pengju is on, he can correct me, but it was on the order of 18 different cases that we've tried to essentially along that injection strategy. It was planned for a number of different fluid properties as well as rock and BFN properties. So these are just 3 of the cases that we ran, just to show you what some of those results look like. They're being post-processed now, final post-processing. But in the upper left, we just took the rock mass with the rock properties that we measured and had essentially a no DFN case. So there's our penny-shaped crack that resulted from this toe stage which I believe injection ran for 8,700 seconds. And I don't have the numbers in front of me, but I believe it was on the order of, I forget how many barrels, but we peaked out at 50 barrels per minute for a period of time. So that is essentially the penny-shaped crack that was that we predicted from the Itasca team in Pengju. In the center here is our base case for rock properties and fracture DFN properties. And at the far extreme, these are all essentially the same bounding box you see in the images. This would be a permeable frictional DFN, so a low strength DFN, the easiest to stimulate. You can kind of see the larger fracture volume that got stimulated in that case. This will be presented in more detail. We'll update the website with all these things, and we'll essentially be informing the stimulation team so they have this kind of information along with some synthetic seismic catalogs that will go along with these when they start actually doing the stimulation in the field. Strain estimates is something we just actually, I mean, this is hot off the presses as of about a week ago, still in process. But basically just look at some of the locations that have been chosen for strain gauges at the site. So we just ran that same toe injection, that injection for 8,700 seconds into the native state model at the toe of 16A. We had to raise the granitoid permeability by quite a bit to get it to take that high amount of flow rate. We did is two anisotropic cases for the permeability tensor on the granite, just to change kind of that shape of that pressure perturbation. And what you're seeing here is essentially the change in displacement in the IJK axes or XYZ. The exact numbers here really I'm not going to comment on, but it's just something that's kind of a work in progress. Essentially our displacements from the order of 10 to the minus 3 and 10 to the minus 4 meters, maybe even less depending on which way we're looking, but fairly small. So quick update there. I don't want to keep too much time for our guest speaker this month. And the topic is actually, it's called a mixed fracture matrix model for evaluating well orientation and completion options for the Utah Forge site. And we actually have, it's quite a large group that presented doing this work. We'll have three, we're happy to have three people presenting it. So Lynn Munday, Jang, and Sam Dhulipala will present here. There are some of my colleagues here at the INL that are taking the lead on this work. So with that, I'll hand it off to Lynn. He can finish his introductions for the rest of his team, and I'll mute myself and get out of the way.
I'm going to start sharing my screen here. And great. All right. So everyone can see this. So yeah, this is a pretty large group.
We see your presenter mode, not the other way. You shared the wrong screen.
All right.
There we go.
Okay, perfect. Great. Yeah. Okay. So hybrid fracture matrix modeling for the evaluation of well completion options. So this is, yeah, a large group has done this work, but this is the group that's at INL that mostly will be presenting today. So so I'm Lynn Munday. Wen Jiang and Sam Dhulipala are also on my team at INL. We're on this computational methods team that mostly implements new numerical methods into this MOOS open source finite element framework. And then there's also a lot of other people in this work. This work was done in close work or collaboration with Andy Wilkins at CSIRO in Australia. And then we're using data from Alita and Branko's teams at Itasca and Golder to do this work. So they're doing a lot of the stimulation and developing the fracture networks that we're modeling. Okay. So the motivation is we need to simplify our modeling workflow to model these discrete fracture networks so that we can efficiently simulate the long-term performance of this geothermal reservoir. So we need to incorporate the data from Golder, which is these DFN realizations that are shown on the bottom left. And then Itasca runs stimulation models with those DFNs in their XSite code. And then Golder takes that data and puts it all together with the Aperture data and everything back onto these meshes. And then we need to run the, I guess, long-term geothermal performance on those meshes that they create. And so, and then in addition to that, we need to do some sensitivity analysis, and that's some of the work that we'll present later is where the production well should be. And then this could all help with, understanding the tracer test that they have planned and some of the other plan for the flow through experiments. So all of this, this work that I'm going to present on this loose coupling algorithm is, it's all available, this open source documentation. Andy Wilkins wrote this up on the Moose website at this website, and it goes into a lot more detail than what I'll present. But so this is all available and written up, and it's also part of the GRC, I think, presentation and paper that we presented there. So this work will be on a loose coupling algorithm that's implemented in this Moose Falcon finite element framework. So one way of modeling these fracture networks we could have a tightly coupled simulation that's shown on the left, where we have fluid flow in the fracture, and that's directly coupled to this matrix. And to do that, we need a conformal mesh. So all of our nodes need to match up, and it's really hard to produce those kinds of meshes for a complicated fracture. Even this simple one is not trivial to produce, even with these TET meshes. And so to simplify that, we can maybe run some type of equivalent simulation where we separate the two parts of our domain into the fracture, and then the other into a uniform mesh, and then have some type of data transfer between them to couple together the energy transfer between these two meshes. And so now I'll go over this loose coupling algorithm. So this is loose coupling. We're modeling these two domains separately. So to do this, we're relying on this multi-app system that's in Moose. So this is kind of a common algorithm that's been used in a lot of other places in Moose, where we have these two separate computational domains, and then we need to transfer data between them. And so other people have implemented these data transfers where they can interpolate temperature fields from our matrix, interpolate that onto our fracture mesh, compute some heat transfer, and then easily transfer that data back to the matrix. And then the solving and everything is kind of taken care of internally in Moose. So we didn't have to do a lot of method development to implement this loose coupling for this. And so this loose coupling has a few underlying assumptions. We're assuming that the matrix properties are not affected by the fracture. So really the matrix can't even see the fractures. So there are no discrete fractures in the matrix. The temperature field flows right through them, like it can't even see the fracture. And we're just transferring that energy is all the matrix sees from the fracture. And then we're also assuming that the flow in the fracture is much faster than the matrix. And this means we can model our fracture network as purely insulated from the matrix. And then it does transfer heat back to the matrix. So that's how they're coupled. But overall, it's mostly independent of it. So doing that, I'll just go through a few of the details of this loose coupling. The first step is we solve for this temperature field in the matrix. Now we're going to transfer this temperature data to our fracture network. And so at our fracture network, we compute a heat flux into our fracture based on this equation I show here, this Q. And we have this, it's just the temperature difference times some heat transfer coefficient. And this heat transfer coefficient is dependent on the matrix element length that fracture is embedded in. So we need to transfer the temperature data from the matrix. We also need to transfer this matrix element length. But that's pretty straightforward to do. The next step is we solve for this DFN mesh, the physics on that. So we solve this finite element model. It has a water equation of state. We're solving this thermal hydrology model, pore pressure and heat diffusion. And we have our permeability right now as a function of our aperture. We're using a pretty simple relationship just for the testing. And we chose, the parameters so that we get, kind of the right permeabilities that we wanted. But in the future, we would want to, have a more complicated constitutive model relating pressure, maybe even temperature to the aperture and permeability. But so right now, one really neat thing about this loose coupling algorithm is that the fracture physics are fast compared to the matrix physics. So that means that we need to take smaller time steps in our fracture, and we're able to do that without having to take these small time steps in the matrix simulation. So we take one matrix step and then we solve like several of the fracture time steps and then transfer that data back to the matrix. So we're able to take a lot more time steps in the fracture, and the fracture for this simulation is a lot cheaper to model than the matrix is. So that gives us a pretty good speed up in our simulation. And then after we solve in our fracture, we transfer the same energy that we transferred to the fracture. We transfer that energy back to the matrix and apply that as these nodal heat sources. And so now we have energy balance and everything's good, and we can solve for our matrix. And then finally, last step is we solve for the temperature field in our matrix mesh. And this completes a time step. And what we can do is we could iterate, we could solve this several times and then have some norm of our temperature field and make sure that that's not changing too much between these iterations. But we've seen that that's not really necessary, but that's something that is implemented in this multi-app system in Moose, so that we could easily do that type of an iteration. We haven't seen a need for it right now. And so we've run a verification problem, and this is written up and available on this this Moose framework website down at the bottom of the page. And this is for this Grin-Garten solution. So this is the fracture domain shown in the bottom right plot, where we have an injection point and a production point on this fracture plane. It's an infinitely long fracture plane, and that's embedded in this infinitely large matrix domain. And then you model just the production temperature over time and compare that to this analytic solution from Grin-Garten. So that's what I'm showing here is, for long times, we get really good agreement. We have a short-term difference, and that's due to the matrix mesh size, we believe. And so with mesh refinement, I think we could get this to be a lot closer for this short-term difference in the temperature field. But overall, this is pretty good agreement. We're happy with this solution. And so move on to a little bit more complicated simulation that uses this framework, where this is a DFN that Elite has given me from Golder, where they have this fracture network. This is still kind of a simple fracture network, but we have 12 fractures in it, and they range in size from 40 to 150 meters. They have a 6 orders of magnitude larger permeability than the matrix that surrounds them. And we're modeling this at 200 degrees is what we're assuming that the temperature field is around this fracture. And then we're going to inject a fluid into it at the green star at 10 kilograms per second at 100 Celsius. And then our production will be 10 kilograms per second. And we'll want to measure how this temperature changes at the production point over time. So for the short-term production, I'll play this video on the left. So what you're going to see is this is a temperature plot of our fracture network. You'll see the temperature, initially it'll be cold from the injection, and it'll travel across our fracture network. So show that temperature traveling across there. I'll pause it right there. So this is kind of the production, or prior to the production. So of the production well. So the production well doesn't activate until the pressure reaches a certain point. And so this was all be this flat region of our curve up to about 1.5 hours. One thing you'll notice is that we initially have a little hump pressure or temperature increase. That's caused by this little sliver of our temperature increasing around our production point in red. So it pressurizes that fluid before the production's activated, and then production is started. And then you see the temperature really drop. And then over a long time, this is the final temperature field for about 1,000-day simulation. And so once production started, you see that we did a mesh refinement study. So that's what all these different colored curves are in the right plot. So for the largest elements, we see a really sharp decrease in temperature initially, and then it flattens out. And then as we go up in coarsening the matrix elements, we see less initial temperature decrease. And that's because over on the left, the heat transfer that we get from the matrix to the fracture is dependent on the matrix element size. So for large elements, we have a slower heat transfer into the fracture. So that means the fracture is mostly initially getting the the production well or the injection fluid is going straight to the production site without heating up that much from the matrix. And so looking at the longer term production, we see that regardless of our matrix mesh size, we're getting kind of the same response at 1,000 days. And then short term, we see a difference, and that's based on this time scale of our matrix elements. So if we look at the time scale that it would take for a heat pulse to travel halfway across one of our matrix elements, we can get an idea of what the time scale is for these different matrix element sizes. And from this, we see that if we're interested in this medium term production of our geothermal source of about 125 days, we really need about a 5 meter matrix element size to be able to resolve that kind of production at the production site for these shorter term production wells. And so this is showing the aperture, which is really just a function of the pressure. So this is kind of equivalent to the pressure field of the final pressure field in our fracture network. But really what we need to do is, instead of using this linear aperture pressure function that we've been testing with, we need to develop a constitutive relation that's based on the X site stimulation data. So that would be probably the next work we do. So this one is showing the cooling of the matrix elements around our fracture network over time. So in white, I'm showing the matrix elements that have been cooled down by the fracture by 10 degrees. And so I'll show that again. I think there's kind of a neat plot movie that Andy made for the web page, but you see the matrix cooling down. And so as the matrix cools down, we would expect some thermal contraction of our fracture network. And so that's something that we need to include when we're computing our aperture, is that change. But of course, if we were interested in kind of the 120 day kind of simulations of 4 months, we would see that the matrix is cooled down about that. So not very much of the matrix is cooled down significantly. So maybe the complexity of our thermal aperture model might not have to be that complicated, but I guess we'll see. So moving on, a lot of the point of this loose coupling strategy was to speed up the simulation time. And one part that takes a lot of time is the computation of the porous flow inside the matrix and solving that part of the domain. So we know we need 5 meter element matrix. And so based on that, we can use automatic mesh refinement. And if we use 2 levels of automatic mesh refinement, we can get 5 meter elements around our fracture network, and then away from it, we can have the coarser 20 meter elements. And that's showing this AMR that we've used here. We can reduce the elements by an order of magnitude. And so I've made a table of just looking at a bunch of different refinements compared to the original mesh, and looking at how much speed up we can get. And so if we compare the 2 5 meter meshes, where one that's this top one, where it's called Refine 2, is just a global refinement. So we have about 70,000 elements in it. And if we use AMR, we have about 7,000 elements, so an order of magnitude reduction, and we get about an order of magnitude reduction in the simulation runtime. And so these are just simulations I ran on my laptop. So they only use 4 processors. They're not really that large of simulations, but we see a nice speed up of using AMR. The other speed up I want to point out is the speed up we get from doing this loose coupling strategy and being able to take multiple time steps in our fracture network when compared to the matrix. So if just comparing a global refinement where we have the 70,000 elements, we see about a 4x speed up if we can take the multiple time steps on our fracture when we compare that to instead of this tight coupling where we take 1 time step on the fracture, that's shown on the bottom. And for every time step we take in the fracture, we also take a time step in the matrix. So this takes a lot longer, about 4 times longer. So, combining these 2 features of this loose coupling, AMR and loose coupling, we get a pretty nice speed up in our simulations. And so, of course, the next work would be to use the real stimulated DFN data from the X site that Itasca has developed. And so Alita has taken that data and she has mapped. So this would be like the kind of data you might get from an X site simulation, where you have all these discrete element apertures and fractures. And Alita's mapped that back to the original fracture planes and then she's mapped the aperture and pressure data back to those original fracture planes, and then put those onto an Exodus mesh output file. So Exodus is a mesh format that we usually use when we're running these Moose finite element simulations. And so now we can read this data into these simulations and run that. And this would also include the extension of these of the original fracture planes and the new elements that's created. So that's kind of the work that we've done, this is the point where we're at with the loose coupling simulations that we've run so far. I guess the next things that we're kind of interested in is accurately modeling this aperture pressure and aperture temperature relationship. And so now I will let Wen Jiang, my colleague at INL, present this work. All right, Wen, you want to start talking?
Yeah, Helen, could you go to the previous slide?
Yeah.
Yeah, thanks. So we're going to talk about a different approach here. As Lynn gave a very good presentation on the loose link coupling strategy for this problem. And as you can see, the advantage of the approach is we can very efficient solve, and we can choose using different time steps, and we can speed up the simulation. And also, it's very simple to use because in the matrix, you don't need to resolve those fractures. But there is one limitation of this loose coupling model approach is that the matrix is a continuous field. We don't model any discontinuity that's created by those fractures. So the approach we did there to account for the aperture is to use some empirical or data-fitted constitutive relationship and give us the opening and the changes in the pressure and the temperature. So the both pressure and temperature can cause the aperture, right? And we feel the better way to compute the aperture is to explicitly model those fracture in those matrix. And because we model the fracture, we could solve the mechanical problem and got the aperture. So that's the reason we switch our gear a little bit to model to using some computation fraction methods in Moose to trying to tackle this problem. So in the Moose, we have already implemented a few methods, fracture methods to model fracture problems. So we have an extended finite element. So it's a discrete fracture representation, and we enrich the shift functions by using some new additional shift functions. And we have used that to model the ceramic nuclear field thermomechanical fracture in 2D, which shows on the bottom left. And we also have the causal zone modeling, which is good tool for modeling delamination. So on a similar manner, we have a discontinuity galaxy. So it's the idea is similar to causal zone method, but it's we have this cesium. You can think of we add this cesium zone everywhere between the element. So it's a good tool for model fragmentation and model the crack initiation. And lastly, and we are working on the facial fracture modeling. It's different than the discrete fracture. It's we say that's a diffuse interface approach, in the sense that our fracture is represented by a variable. That's a diffuse variable. And on the bottom right, we just show we also use this phase field to model the field fragmentation of the 3D field palette on the thermomechanical conditions. So, a very good thing or the advantage of phase field fracture model is it can handle the nucleation and the propagation automatically, and we don't need to worry about the change of the mesh, and we can use the same background mesh and we just solve this phase field. And it handles propagation of the crack as well, and also complicated, as you can see on the bottom right. It can handle very complicated branching or merging of the crackers. So that's one of the reasons we start to use phase field fracture in this work, in this project, to try to compute the aperture. And it's easier to implement in Moose, so that's another reason we use that. So next slide. Okay. So, so the first thing we want to do here is we still want to use this 2D discrete fracture network mesh that Lynn generated or used in the Munday app. So we want to use that as a starting point, and we use that to initialize our phase field damage variable. So on the bottom left, as you can see, so I visualize you can see the 2D discrete fracture network mesh, yeah. And also I also plot the contour of our damage variables. So you can say the contour is almost same as the mesh. So that means our algorithm to compute the initial phase field variable is right and very robustly to get the shape or the initial damage profile. And one thing about phase field is it has we need a damage variable, right? And we want to resolve the damage variable as much as we can. So one way is to use adaptive refinement. So for this case, we use 5 levels refinement to refine very thin fraction representation. And yeah, so that's very efficient because we can isolate we use a very small number of elements just near those fracture networks. And the remaining the matrix, we can still use a large element size. So yeah, that's the way we initialize the phase field damage variable in this work. Next. And once we have the phase field damage variable, so which is shown on the left. So damage variable will goes from 0 to 1. So 0 means there's no damage, and 1 means the damage, there's a damage, right? And it goes from 0 to 1 very steeply, as you can see on the bottom left. And in the matrix, there's no damage. And we use this damage variable so to get some degradation functions. So the degradation functions can be used to, for example, reduce the elastic constants for mechanical part, and also to reduce the thermal conductivity for the thermal part. Just to give an example, which show on the bottom right, is the thermal conductivity. So you can say within the fracture, we have a very small thermal conductivity. So with using this small thermal conductivity, we kind of doesn't allow the heat to transfer across the fracture, so across the fracture surfaces. So, so this is an isolated fracture condition, right? And but we can also implement other heat transfer across the fracture surfaces in the future. But that's just one of the demonstration of how we use phase fields in the thermomechanical problems. Next one. So, and this is a very preliminary demonstration problem. It's a thermomechanical problem. So the purpose of the example is we want to say we want to show that we can use this approach to compute the aperture for this little bit complicated networks. So for this problem, we have a symmetric BC on the blocks, and we fix the top and bottom. And to mimic the cooling due to the fracture and on the matrix, and we apply a uniform thermal expansion to the matrix in this case. So the expansion is negative, so that's caused the contraction of the matrix because we fix the bottom and the top. So the fracture surface, you will expect that due to the contraction of the matrix, it will pull the fracture, and it will cause the opening of the fracture. Yeah, that's the reason you see. And the top of the fracture surface, you can see the positive displacement, and below the fracture surface is negative, right? And from this, we can actually very accurately compute the fracture aperture. And this is and also on the right, we can show due to the fracture networks, we can see the stress concentration at the crack fronts. So in this work, we haven't really evolved our damage, and we just put the stationary crack to show this case, to show our preliminary capability. But in the future, what we plan to do is to make the crack to propagate based on certain criteria. That's one for the crack propagation. And also we want to couple this thermomechanical with the fluid solver to compute the fluid flow within the fracture networks. And the fracture networks will cause the pressure, and both the pressure and thermal contraction will cause the opening, and they will cause stress concentration and therefore cause the crack propagation. So that's what we have so far. And we think the phase field is a promising approach. At least it can give us the accurate aperture calculation. And we can either couple that still using the loosely coupled approach, or we can have a fully coupled approach, like I said, solving the fluid and the thermomechanical problem within the same map. We will decide those later. We will do some of the evaluate computation cost for various coupling strategy. But this is a good starting point, I think, for us to extend our work to real problem and to get the aperture and propagation to work in the future. That's all I want to present today. Thanks, Lynn.
Thanks. Yeah, thanks, Wen. And so the next part of the presentation will be by Dhulipala. And once we get these simulations running quickly, we need to know where we would want to place the production well. We'd want to do that in kind of a statistical manner that we might not actually know where it is. And that would be useful for the experimental planning and just the operational conditions for thermal energy recovery. So Sam, I'll hand it over to you. You can talk a little bit more about this and tell me when to flip slides.
Yeah, thank you, Lynn and Wen. Earlier in the presentation, my colleagues presented about the discrete fracture network model and also an explicit approach for modeling fractures. In this part of the presentation, I will talk about optimizing the production well placement such that the geothermal energy output can be maximized. So there are 2 points to note here. The first point is, instead of deterministically locating a single production well placement, we are trying to find the ensemble of production well placements that are all equally admissible, or that all result in geothermal energy outputs exceeding a certain threshold. And the second point is the computational expense. When we solve these optimization type problems, we will typically call the model numerous times. And the model itself can be computationally expensive, which can put constraints on the degree and the accuracy of our optimization. So to address both these issues, that is finding the ensemble of production locations as well as dealing with the computational efficiency, we're planning on using an adaptive sampling approach, which is a statistical approach for finding the ensemble of well placements. Next slide, please. So the particular type of adaptive sampling we're planning to use is known as parallel subset simulation. As shown in the figure in the bottom left, parallel subset simulation is a stochastic optimization and failure analysis algorithm. How it starts is that it starts by simulating some Monte Carlo locations of the wells on the fracture planes, and then simulates the model output. From those Monte Carlo simulations, the algorithm identifies those production locations that are leading to the highest output from the geothermal system. So once it identifies those production locations, it will initiate numerous Markov chains such that the Markov chains will even optimize the solution further. All these Markov chains are shown in these arrows, and the different colors represent different subsets, which means as we are progressing towards the second subset to the third subset and so on, the output from the geothermal energy system will only increase, it will not decrease. That is one of the features of the algorithm. On the right-hand side bottom, we see an example output from this parallel subset simulation algorithm. The different colored bands here represent the model outputs in different subsets. As you can see, as we are going from the blue band towards the gray band at the top, the model output is only increasing. But also, we're not getting a single solution for the optimal point. Rather, we're getting an ensemble of solutions. For example, in the gray band, we're seeing some uncertainties, and that those uncertainties will be associated with corresponding extraction points or production points on these fracture planes. So we're getting an ensemble of solutions from these from this algorithm. But also, in terms of the computational efficiency, all of these Markov chains shown towards the left bottom can be run independently on several processors or an independent set of processors, which means even if each model evaluation takes about 40 minutes, we can come up with the optimal ensemble locations of the extraction points in about 1 to 2 days using 1,000 processors. And we can also extend this algorithm to go further. Next slide, please. So one of the key things for this parallel substrate simulation algorithm to work is to be able to sample on these fracture planes. On the top, I have a representation of the fracture plane that Lynn has given me. What we did first is that we implemented a version of the fracture plane sampler in the Falcon app. The fracture plane sampler actually idealizes each fracture plane currently as a circle and then samples randomly on these different circles or fracture planes. And these coordinates of the location or these coordinates of the extraction locations will then go into the discrete fracture network model, and then we will get an energy output. And that energy output will be taken by the parallel substrate simulation algorithm to optimize the solution further. Although we are idealizing these fracture planes currently as circles, in the future, we will alleviate this assumption by using a more sophisticated technique called kernel density, which can take into account any arbitrary shape for the fracture plane. Next slide, please. So before using the parallel substrate simulation sampler, we ran a test case with a simple Monte Carlo by randomizing the extraction locations 10 times on the fracture network that we showed in the earlier slide. So this is to test our information transfer from the Monte Carlo driver to the sub-app 1 to the sub-app 2. Sub-app 1 does the matrix modeling, and the sub-app 2 does the DFN modeling. So for these 10 random production locations, the top figure shows the temperature output, long-term temperature output with respect to time. And we see that different production locations can result in quite a significant different temperature outputs. On the bottom, we show a histogram of the output energy in joules for these 10 random production locations. So this kind of verifies that our Monte Carlo driver is working satisfactorily. And we are in the process of transferring this Monte Carlo driver to use the adaptive sampling, that is the parallel substrate simulation sampler, to optimize the production location further. I will then now hand it over to Lynn to discuss the conclusions and future work. Thank you.
Well, thanks a lot, Som. That was nice. So future work would be to use the stimulation data developed by Excite and Itasca and Golder, and to be able to use that to do some of these, plan the flow through experiments and understand the tracer tests, and then just overall for operational modeling. So, Rob, that's the end of it.
Thanks, Lynn and Wen and Som. So it is 1:15. We have some time for questions. I didn't see anything show up in the chat, but if you have a question now, actually, if you want to, you can even, since there's nothing in the chat, if you want to just speak a question, I'll give it a moment. Otherwise, I'll start providing some commentary. So a question came in: are there any limitations for phase field modeling?
Yeah, Wen, would you answer that?
Yeah, so I would say every computation method has some certain limitations. I mean, I can only tell you the limitation of the phase field compared with other approach. Lynn, could you go back to that slide where for example, let's talk about computation cost for this various approach. in general, phase field fracture will be generally more expensive than other approach because, like I said, the phase field variable, damage variable, it goes from 0 to 1 smoothly, but very steeply. So we need quite a lot of elements within the fracture zone to resolve that steep transition. So, and that approach can be alleviated by the mesh refinement to some extent. That's one of the limitations of the phase field modeling. Another maybe a little bit a challenge for phase field is since we are not opening up the fracture. Lynn, could you go back to the last slide for fracture modeling? Yeah, so yeah, you can say we have the displacement, we can compute the displacement jump, right? And that's give you the aperture. But the things we are not exactly model the opening, or I mean, we don't create, how do you say that, break the mesh between the matrix or at the fracture surfaces. So the aperture needs a little bit of work to get the more accurate. So it does, it's not a limitation, but just something need a little bit research work to get it right. There are some already reported methods to compute the aperture. Mainly they are using phase field for hydraulic fracturing, like the work done by Meriwether in UT Austin. There are several ways to compute the aperture, but personally, I'm feeling there might be a better way, and I'm working with another colleague at our group to get the aperture more accurate. So I won't say that's a limitation, but just like an interesting research topic. And yeah, and compared with this limitation, the advantage is so obvious. So we can model the nucleation, cracker propagation, multiple cracks interaction. That is a very good advantage of the phase field. Yeah, I hope I answer your questions. If you have more questions, please let us know. Thanks. Thanks, Lynn.
Yeah. Thanks, Wen. So we have a question for Herman. How was the DFN defined? So I see that Alita Finella is on. I'm going to pass on to her. She's our lead. She's with Golder Associates, and she's been leading all of our work for defining, characterizing, and sharing all of our reference DFNs. So Alita, can you help answer that question? I know I can answer it, but I think you'd probably do a better job.
Yeah, sure. So I think there's been extensive work in defining the parameters for the DFN. So over the years, we have a lot of data coming in from image logs and similar terrains in the nearby mountains. So and actually we had a couple presentations on developing the DFN. I think the July modeling presentation is recorded that you might find helpful. But so we have sort of this reference DFN, and we created 3 realizations for the stimulation work. And what you've seen in this presentation is just a small 10 fracture cluster from one of those realizations to use as the initial testing that you've seen here. What the next step is fully translating the 3 realizations from that were used for the stimulation work, and then passing those on to Lynn for this work. So you're not seeing the full DFNs for the site here. You're seeing just the small sort of 10 fracture sample that's been used for testing. Any specific question about it?
I think that covered it pretty well, Alita. I'm gonna take over the share for one moment, if it'll let me, and just to further that, Alita, so we can show it. So I think this gets to like what some of those cases might want to look like, as far as some of the outputs from what Alita would hand a reference DFN to Itasca, which they would do a stimulation model using their code X site. And essentially what you're seeing is a number of the kind of the stimulated fracture networks that we get back. That's getting reprocessed and handed off to Lynn to be done in this continuum-based method. Does that help at all? Okay, I'm gonna try to get back here and get back to seeing all my controls. Herman, if that doesn't answer your question, follow back. Okay, oh, gotcha. Okay. Mark McClure. So yeah, feel free to unmute yourself. If you have multiple questions, it'd be easier.
Yeah, thanks. Yeah, I guess I'm curious, looking forward, what you guys are thinking about the coupling between the fluid flow and that phase field. And I guess a related question. So, a standard boundary condition on a mechanically open crack is that the fluid pressure equals the normal stress. You've got to solve this coupled system to find, the distribution of apertures everywhere that satisfies that boundary condition everywhere. And that creates a really tight coupling of the mass balance equations and the fractures with the deformation equations. But it seems like so far, with the loose coupling strategy, you're doing a lot of like passing back and forth between meshes. So I'm kind of wondering how you guys are thinking of architecting that coupling as you start to put it all together.
So I could probably answer that to the degree you need for right now. So the loose coupling method we put together because trying to make a fully conforming mesh with the complexity of the DFNs that you see on my screen, we went down that road, and I think many others have also tried, and we just found it to be, essentially a very tenuous and maybe perhaps untenable problem. So what we need to have is a way to actually get some kind of information, mostly focusing on heat transfer. So for the multi-app part you're seeing, it's not necessarily meant to accurately, to the degree of the tight coupling you mentioned, solve for mechanics in this system. So you'll notice that in that system, we're solving for pressure and temperature. And because the mechanics solve is very expensive. So if we could use an analytical solution or semi-analytical solutions for changes in aperture based on pressure and or temperature, that was the initial goal of that. So we can get a lot of results and try to provide information for the most optimum well placement given a DFN, hopefully where we get good data from a microseismics for locations. So we have a good idea what our connected fracture network is, originating from the injection well, so we can help place the extraction well. But in doing so, we've been struggling to try to get that thermal stimulation part in a very simple closed form kind of sense, as I'm sure you're aware. So that's where we essentially, enlarged the team and asked for some input from our larger computational mechanics group, where Wen came in. I just postulated a question to them to help me come up with a way to get a better representation of this. So I'm not sure that's answering your question or not, but I could actually ask Wen to weigh back in, or Lynn to take it further from there. But maybe you want to follow up, Mark.
Oh, okay. I don't know. I guess just I'll comment that, if the fracture walls are in contact, then yeah, you're pretty safe, pretty much decoupling. And you could use like a local calculation, from the local stress and pressure, you can calculate aperture. But when the walls come out of contact, it becomes this like kind of more globally coupled problem, because like the stiffness of like a crack, for example, depends on its size. And so like, if you only know information about a given element, you really don't know its stiffness. If the crack is open, you need to have like a coupled solution of a system. So anyway, that's something to just think about, because it's a tricky part of the problem. And I guess another comment, I'm just because I work in this, I'm just kind of brainstorming, or ideas are coming to my mind. But another one is I've moved towards basically using a non-conforming grid for the reason you've illuminated, that it just gets extremely challenging as these things advance to go with totally conforming grids. So I totally understand that.
Yeah,
You can use like multi-scale type effects to subgrid within elements and handle discretization artifacts.
okay.
So I guess one thing about the phase field approach, Wen can say more about this, is that so our element sizes were like 0.3 meters, which that's really, that's a lot bigger than an actual fracture. But some of the phase field formulation has it built into it to actually it converges to the actual effects of the fracture faster than the actual mesh refinement. So even though our element sizes might be large, we can still get the effect of that discrete fracture. What exactly did you tell me about that? I forget.
Yeah. I think there are some new development on the phase field fracture model. Is the length scale to control the size of the phase field. We can make it a purely just numerical parameter. So based on your computation resources, you can potentially use a larger or a thicker phase crack crack weights or thickness. And you can also, if you have a finer or you have a more computation resources, you can use thinner. So they won't affect your solution. They will give you the good similar or very more accurate results compared with the older or previous formulation. So based on the loosely coupled strategy, I just want to add one more comment. We show phase field. I didn't emphasize the extended finite element. So that's I think that's another way to go in the future. We did some implementation for 2D. You can see the field palette cracking. And there is a 3D. We have all the code there to do the 3D, and we can model the stationary 3D. But there is something we need to do is to do for example, the intersection of the cracks. So if that can be sorted out, in my opinion, XFAM can be another good alternative for this problem, because they provides you some surfaces and you can apply the pressure, and you can reuse the loosely coupling strategy. You can solve a fluid problem on subsurfaces. And in the matrix YS level, you can use XFAM to introduce discontinuity and do the propagation. I would say there are a lot of challenge there, but that's potentially an ideal solution, computation cost-wise and other yeah, I think it's just better solution. But we haven't still decided which one to go. Like we said, the choose phase field is really just simple to implement, works in both 2D and 3D. Yeah, we will see how much we can go from there.
Thanks, Wen. Actually, there's a follow-up question here from Herman.
Thanks, guys.
Can you comment on the volume constraints of the phase field model? And
yeah. Herman, can you be a little bit specific on what volume constraint you're talking about here?
Yeah, come off mute, Herman. Just ask your question.
Yeah, quick comment here. Yeah, I was thinking about it when I saw your animation with this the 2D animation, which was pulsing like a heart. And so you on that graphic, at least you introduced a lot of volume by opening your fractures dynamically. And the question is how that is basically feeding back into your pressure requirement, and then in your boundary condition for the model. So how you set the model, how is it open on the sides, is it expanding, or is it free on the top surface, and so forth. So that was
you were talking about the volume inside the fracture, right?
Yeah, yes.
Yeah, great. So, yeah, so the picture, the 2D is actually with XFAM, it's not phase field, but on the right is the phase field. But I can come back to your question, I got your question. So for hydraulic fracturing, I mean, I'm more familiar with that because I read field literature in that area. I think they share similar physical concepts between these methods. So usually when you have the Lynn, could you go back to the last slide of our phase field simulation? Yeah, you can see like we can we have a zone. You can think about phase field approach. We have a fracture zone. So we're going to solve a fluid problem within that fluid zone or fracture zone. So that zone will, the fracture flow will depend on the opening, the aperture directly computed from the phase field simulation. And the orientation or the flow direction will be, we will align that with the fracture networks. And in terms of the boundary conditions, so since the two models, they are not decoupled, they are in the same mesh. So their force balance is automatically enforced. So the pressure applied on from the fluid, we automatically applied on the matrix. And yeah, so that's good. We are going to solve a coupling system of the fluid, thermal, and mechanical in a one system or in a one mesh. Did I answer your questions or?
Yeah. I see how you do that. So, but the question is for me also how you compensate for that opening. I mean, that's in the next step, and when you open really your fracture, at the moment you have a static fracture system. Is that correct?
Yeah, exactly.
Oh, okay, good. That's a difference. Because
Okay, thank you. Thank you for your question.
Thank you. Sorry for that.
Yeah, no.
No worries. That's why we do these. I don't see any other questions in the chat, so I'll open it up to for last parting questions or comments. And while we're waiting to see if anything comes in, I want to make just one comment here, is that all this code that was shown, everything we're doing here is all open source. Some of it and it's all available on GitHub. If some of these things may be in private branches right now, as we're still developing some of the linkages, but if anyone's interested in using or trying or working with these things to help us to work through some of these issues or look at it, feel free to reach out to me, and we can get you into there, like most likely. And I think a good example is I see Bud Johnson is on here from NREL. Lynn showed a slide earlier for the grid garden solution where one of his colleagues reached out to us for some of these capabilities, and we shared the code. They took it and ran. So this work was done by one of Bud's colleagues at NREL, and that was who was that, Lynn?
Conrad Becker.
Conrad Becker's. Yeah. So, and actually, we actually made a full example in the Falcon suite. You see the link there at the bottom. So actually the code and the write-up for that is there. So you could actually just check that out and run it yourself and play with it in different ways if you're interested. So I'm not seeing other questions. Go ahead, Lynn.
Oh yeah, so all of this code is definitely in the repository. If you pull Moose, you can get this. But and this stuff that Wen has done, that code, Wen didn't really write any new code. This was already mostly there. So this was just a matter of importing this fracture network and running this.
Okay.
And I think with some of Som's work, we do have some development work that we need to do to be able to take samples based on a geometry of a fracture network. But these underlying algorithms, I think Som has recently merged into Moose.
Thanks, Lynn. And thanks to all my speakers. Thanks to our guests here today. With no further questions, we'll adjourn, and hopefully we'll see everyone next month. For those of you that are in the US, happy Thanksgiving. Hope you enjoy your holiday next week, and look forward to hearing from everyone soon. Thank you. Yeah, Gosha, I think you could close it out and save the recording. There's a few people are still on. I'm betting they may have walked away from their machine or nodded off. They heard me, they're dropping off. Thanks for joining us today.